Welcome back to the Deep Dive. Today we're giving you, well, the ultimate shortcut to understanding how businesses and scientists actually prove their claims. We're going beyond just simple averages. We're diving into statistical hypothesis testing, the framework they use to decide if a new drug works,
Right.
or if a marketing campaign really moved the needle.
Right. Or if a belief you've held for years is actually wrong.
Exactly. Our mission today is simple. Distill this entire framework. We're going to cover the battle lines, how you control your risk of being wrong, and the two major ways you make that final evidence-based decision.
And we're going to give you the concepts, not just a bunch of formulas.
Okay, let's unpack this.
When you really strip it all down, hypothesis testing is. It's just a process of setting up two competing statements about something in the population.
Like an average rating or
Yeah.
a percentage of customers?
Exactly. And then you use your sample data to see which statement the evidence supports. We always start with the assumption, which we call the null hypothesis, or H0.
H0. Okay, and that's the status quo, right? The default assumption.
Precisely. It's the no difference or nothing has changed claim. You can think of it like the assumption of innocence in a court of law. It's what we test under, and it always includes the statement of equality.
So if a company has always said their widgets last 10 years on average, H0 is just,
Yeah.
the average is still 10 years.
You've got it. It assumes no change until proven otherwise. And then you have the challenger, the alternative hypothesis, or HA.
This is the new idea,
Yeah.
the thing you're actually testing for.
It's the research question. And we only reject that status quo, that null hypothesis, if the evidence is really, really convincing.
And the way you frame that alternative hypothesis,
Yeah.
that actually shapes the whole test, doesn't it?
It does. If you just suspect the widget lifespan has changed, maybe up, maybe down, you run a two-tailed test.
But if you have a specific suspicion, like a new process made them last longer than 10 years, that would be...
A one-tailed test, yes. Your alternative hypothesis defines whether you're looking for a change in one specific direction or just any difference at all. That directionality is crucial.
Okay, that structure is vital. But let's talk about the elephant in the room.
Right.
We're using samples. They aren't perfect.
No, they're not.
So we're making these big decisions based on a tiny snapshot, which means there's risk involved.
Correct. And this is where you have to decide your tolerance for being wrong. The first and most controlled risk is the type I error.
A type I error. What is that exactly?
That's when you conclude there is an effect when in reality there isn't one. You reject the status quo when it was actually true.
So in business terms, that's launching a new product thinking it's better, but it's not. That sounds like a false positive, a very expensive mistake.
It's often considered the most damaging one, which is why we control it right up front. The probability of making this type I error is called the level of significance, or alpha.
Alpha, I've seen that.
Before you even touch the data, you have to set your alpha. Usually it's something small like 5%, maybe 1%. You're formally stating, I will accept, at most, a 5% chance of making this specific mistake.
Okay, wait. If this error is the worst one claiming success when you failed, why don't we just set alpha to be incredibly tiny, like 0.00001%, just avoid being wrong?
That is a fantastic question, because there's a trade-off. The moment you make it extremely hard to reject the null hypothesis, you dramatically increase the chance of making the second kind of error, the type 2 error. This is the error of missing an effect. It's failing to reject the null hypothesis when the alternative was actually true. You missed the discovery. The drug worked, but your test didn't see it.
So setting a really strict bar to avoid a false positive means you're much more likely to miss a real discovery. That's the core tension here.
It is. You are constantly balancing one risk against the other. And this tension is exactly why we use very, very careful language.
What do you mean?
You will never hear a seasoned statistician say they accept the null hypothesis. Never. They say do not reject it. It's the difference between declaring someone innocent versus not proven guilty. We're acknowledging that we might just not have had enough evidence. We haven't eliminated that possibility of a type 2 error.
That distinction. That really clarifies the whole process. So once we've set our hypotheses and our risk level alpha, we need a way to judge the evidence.
Right. We need a measurement, and that's our test statistic. It's basically your standard scoreboard. It tells you how far away your sample result is from what the null hypothesis claimed it should be.
And if that score is huge, it means your sample's way out in the tail. It's unusual.
Very unusual. And we have two main ways to interpret that score: the p-value approach and the critical value approach.
Let's start with the p-value approach. This is what all the software spits out. How should you and I think about a p-value?
The p-value is the probability of seeing data at least as extreme as what you actually collected, but, and this is the key part, assuming the null hypothesis is perfectly true.
Okay, so if that probability, that p-value, is super, super low,
like 0.001,
it means the data I collected would be almost a miracle if the status quo were correct.
You've got it. It's like the data is screaming, I don't belong here. The null hypothesis must be wrong.
And that gives us a really simple rule then.
A very simple rule. If the p-value is less than or equal to your alpha, your risk level, you reject the null hypothesis. The evidence is too rare to be just chance.
Okay, that's the p-value. Now contrast that with the critical value approach.
This method is a bit more old school, but very intuitive. Instead of calculating a probability, we establish a cutoff point on that scoreboard axis. We literally draw a line in the sand.
A line in the sand based on our alpha risk.
Yes. That line defines the rejection region. If your calculated test statistic, your score, lands past that line, you reject the null hypothesis. It's just too far out there to have happened by chance.
So one is a probability, the p-value, and the other is a specific point on the axis, the critical value.
Exactly. And for two-tailed tests, you just have to be a little careful. You have to split that alpha risk between the two tails. So if your alpha is 5%, you put 2.5% in the upper tail and 2.5% in the lower.
But the big takeaway is that both methods will always lead to the same final decision.
Guaranteed. They're just two sides of the same coin.
Okay, let's make this real. Let's see this in action with an example for a population mean using the t-statistic. This is the bread and butter of business stats.
It is. Our scenario is Heathrow Airport. A business travel magazine wants to classify an airport as superior service if its population mean rating is greater than 7.
So we're testing for superior performance. Our null hypothesis, the status quo, is that the mean rating is 7 or less.
And the alternative, what we're hoping to prove, is that it's greater than 7. An upper tail test. We'll set our risk, our alpha, at 0.05.
Okay, so we get the data. A sample of 60 travelers. Their average rating was 7.25, with a standard deviation of about 1.05.
And when you plug that into the formula, the t-statistic R-score comes out to 1.84.
So let's use the critical value approach first. What's our line in the sand?
For a 5% risk level with this sample size, our critical t-value, our cutoff, is 1.671.
And our score was 1.84, so we're past the line.
We are. It falls into the rejection region. An average of 7.25 is just too high to have likely happened if the true population average was still 7. We reject the null hypothesis.
And the p-value approach has to tell the exact same story. What's the probability of getting a score of 1.84 or even higher?
The p-value for that is 0.0354.
And since 0.0354 is less than our 5% risk threshold,
the conclusion is identical. Reject. The probability of this being a random fluke is less than our acceptable risk. So the data provides significant evidence to classify Heathrow as a superior service airport.
Right. It's not just that they happen to sample 60 happy people. The evidence is statistically strong.
Exactly. Now let's switch gears to a slightly different question. A test about a population proportion.
Okay, so not an average anymore, but a percentage. Like what percentage of voters will vote a certain way?
You got it. And for this, when the sample is large, we typically use the z-test statistic. Our scenario is the Pine Creek Golf Course. They ran a promotion to try and increase the proportion of women players, which historically was 20%.
So the null hypothesis H0 is that the proportion is still 20% or less.
And the alternative, HA, is that it's now greater than 20%. Another upper tail test, and we'll stick with alpha at 0.05.
Okay, so what did the data show?
They sampled 400 players after the promotion, and 100 of them were women.
Okay, so 100 out of 400, that's 25%. So the sample proportion is higher. But is it high enough to be significant?
That's the question. When we calculate the z-statistic, that scoreboard number, it comes out to 2.50.
Wow, a z-score of 2.50. That feels pretty far away from the center.
It is. Using the critical value approach, our line in the sand for a 5% risk level in a z-test is 1.645.
And we're at 2.50, so we are way past that line.
Way past it. We reject the null hypothesis. The sample result is just too unlikely to be a fluke.
And I'm guessing the p-value is going to be tiny.
Yeah, very tiny. The p-value is 0.00062. That means if the promotion had done absolutely nothing, there was only a 0.62% chance of seeing 25% women in a random sample. The evidence here is what we'd call overwhelming.
So the promotion definitely moved the needle. The decision to reject the null is well, it's undeniable.
It is.
That sums up the whole process perfectly. No matter what we're testing, a mean or a proportion, and no matter which approach we use, key value or critical value, the framework is the same and the conclusion is the same.
You've got the toolkit now. You define the claims, set your risk, measure your sample's deviation with the right test statistic, and then make the call.
So what does this all mean?
It means you are now equipped to skeptically analyze pretty much any statistical claim you see in a business report or a news article. We spent this whole deep dive focused on how to reject the status quo when the evidence is strong.
Right.
But here's something to think about as you finish this deep dive. Hypothesis testing gives us a binary yes or no answer about one specific number. Is the mean greater than 7? Yes. But this idea is very closely related to interval estimation, or confidence intervals. So consider this. How does finding a whole range of reasonable values for the population mean complement this yes or no test? If the null hypothesis value falls outside that confidence interval, you'll always reject it. Understanding how testing and interval estimation are really two sides of the same powerful coin, that offers a much richer layer of context to your decisions.